We are going to now show an example how to solve a deterministic model of optimal resource allocation. We have in this problem a discount factor beta. So we will assume beta is actually bigger than 0. We don't have to at this moment to assume beta is less than 1, but we know usually a discount factor is less than 1. All right, this is actually a rather ordinary optimization problem we have actually encountered in Calculus 1. But in this problem, we have new situations, a parameter inside, so we need to be more careful. So let's just start slowly, and we will try to recall what we did in the past. Okay, so we're going to try to find a solution. Okay. The first step is to find the beginning, the starting value. So we say this is the resource allocation. So if we have just one period, then if we have a total amount of A, and then this is going to be the maximum, x is between 0 and A, we allocate x amount, and we try to find out what's going to be the maximum utility. And we have a utility function with positive marginal utility. So we are going to actually see that our optimal resource allocation is simply going to be capital A. And how do we do that? We can, of course, just say the function is increasing, but how do we do that? We say, well, look at this function f of x is equal to 1 minus x, right? And we try to take the derivative. That's the normal procedure. And then we have 1 over x squared bigger than 0. So we don't have any critical value between 0 and A. So what it means is that f of x is simply increasing when x is between 0 and A, right? Because it's increasing, so f of A is the largest. F of A is equal to 1 over A is the maximum. It's the maximum, right? So what it means is that V1 of A is going to be simply 1 minus 1 over A. So this is the starting point. Now, after this one, we're going to find V2. Let's first write down the formula. So V2 of A is going to be the maximum. Again, this is so-called an absolute maximum problem. And then we have U of X. This is the utility we gain from allocating X to the first period or the present period. And then plus the utility of future beta over here. And we have over here is the optimized future utility. Since we have already allocated X to the first period, so we only have A minus X left. Okay, so this is what we have. And then we plug in the formula. So this is going to be the maximum. X is between 0 and capital A. The utility function is 1 minus 1 of x, and then plus beta over here. And here we need to be very careful because we have the formula for V1 of A, but we are plugging in capital A minus x. So use the formula of V1 of A, we have 1 minus 1 over x, A minus x. Okay. And if we want to, we can just call this a new function. So let me call this one over here. This time f of x is equal to 1 minus 1 of x and plus beta and 1 minus 1 over A minus x. We still follow the idea from calculus. In calculus, we learned how to find absolute maximum. We take the derivative and set it to 0. So f prime of x takes derivative negative 1 over x. Derivative becomes 1 over x squared. beta derivative is 0, and we also have the second one. So this time we need to be extra careful. If we take the derivative of a minus x, this is what we have. We have negative 1 over a minus x squared and times negative 1. This is important because of the chain rule. Here we need to always remember the chain rule. And then because another negative sign in the front, so we have negative beta, and then we're going to have negative becomes positive, and then we have a minus x squared. Okay, so that's the one we have. So now we're going to try to see if we have a solution in the interval. So set this one to be 0, and we have 1 over x squared minus beta and a minus x squared, and it's equal to 0. Now, we usually see a nonlinear equation. So how can we solve an equation like this? The easiest way we see is that move one term to the other side. So we have, we see that 1 over x squared is equal to beta over a minus x squared. Okay. Once we have over here, then we can take the square root. Remember, x is bigger than 0, right? So beta is bigger than 0, and a minus x also bigger than or equal to 0. So then we take the square root. So to make sure that you get the signs right, take the square root. And then we have 1 over x, which is still positive. And then here we get root beta. And then we have 1 minus x. Different equations are solved differently. So we just need to be very observant how to solve this. Now we have fractions. So we're going to do the cross product. So what it means is that you're going to multiply a minus x both sides. And then multiply x both sides, then we're going to have actually x times beta like that. And then we try to collect like terms. Just be very careful. This is going to be beta square root of this x. So we will have 1 plus root beta x is equal to a. And x is equal to a over 1 plus beta. And remember, this is our critical value. This is our critical value. Now, you need to check. Usually, this is the case. Need to check if this x, let me put it in an asterisk over here. Need to check if this one is inside 0a, because we are taking maximum between this interval. Okay, so, and obviously, a over 1 plus beta is bigger than or equal to 0. That's okay. And also a over 1 plus root beta, because this one over here is going to be less than a over 1, because beta is 0, right? Beta is bigger than 0. So this is less than that. So what it means is that x star actually is inside 0a. In fact, we see that it's strictly inside. Okay. So now, what it means is that this is a candidate for maximum. So x star equal to a over 1 plus beta is a candidate for the maximum, right? And how can we be sure it's maximum? We need to use some kind of tests. Now this time derivative isn't too bad, so we're going to take the second derivative. We use the so-called second derivative test. But in other cases, you can use other kind of tests, like try to determine the concavity using derivatives, whether it's increasing or decreasing, and other methods. So let's use the second order derivative test. Second order derivative test. Let's go back a little bit to see where the derivative is. The derivative is over here. Okay, so we are going to take the second order derivative. F prime of x is 1 over x squared minus beta a minus x squared. So if you take one more derivative, then this is going to be x to negative 2. So you can have negative 2x cubed. And here, just remember the chain rule. And then this is going to be also negative 2 and a minus x, negative 3, and then we have negative 1. So we end up with double derivative is going to be negative 2x over x to the third, and then we have minus 2 beta and a minus x cubed. We have that second order derivative. It's less than 0, so x star equal to a over 1 plus beta is the maximum. Is the maximum point for the value for v2 of a. For just f of x. For f of x. Okay. So once we find x star, then we can find v2. So plug in x star into 1 minus over x and plus beta v1 of a minus x, we have the maximum. We have v2 of a. And just do the computation very carefully. So this is the detail what we have. So we do it slowly. So x star now is a over 1 plus beta, right? Beta over here. So 1 over x star is going to be 1 plus beta square root over a, right? And a minus x star, and that's going to be equal to a minus a over 1 plus root beta. If we use the common denominator, and that's factor a out, and then we're going to have 1 plus root beta over here minus 1. So we have root beta a over 1 plus root beta. So all these details we need to go through. And then remember what v1 of a minus x is. This is 1 minus 1 over a minus x, right? So if we plug this one inside over here, then we have 1 minus, again, it's 1 plus root beta over root beta times a. All right, and it's not done yet. This is root beta. Okay, so now we plug everything into it. So we have v2 of a. It's going to be 1 minus 1 over x star, which is 1 plus root beta over a. And then plus beta, and this v1 of capital A minus beta. So this is the one we have over here. 1 minus 1 plus root beta over beta A. Okay, we have to simplify if we want to actually continue and find a pattern. So this is what we have. We will have 1 minus 1 plus root beta and A over here, and plus beta and minus. If we look at what we have, we cancel 1 square root of beta, so we have root beta, and 1 plus root beta, and over A. Okay, and we somehow put like terms together. This is a constant term. Remember, A is our parameter, so we have 1 minus. If we do it carefully, we have 1 plus root beta over here squared, and that's over A. So that is V2 of A. Now, let's look at what we have for V1 of A and V2 of A. And also try to simplify the notation. Let's go back over here because you have seen in the notes that we introduced another parameter alpha over there. And the motivation to introduce another parameter is over here. If you look at what we have over here, when we solve the equation, we get actually square root of beta over here. Yes, over here. So if in the original equation, if we actually call, say, if we call beta to be alpha squared like this, then when we take the square root, we have simply over here, this is going to be alpha. And then we don't have this cumbersome square root to carry around. So our solution will be simply x star is equal to 1 over a over 1 plus alpha. So that was the motivation. So it's unnecessary, but on the other hand, it makes algebra looks simpler. So we can actually make this change of, so we're going to call this beta is equal to alpha squared, and then this is what we have in terms of alpha. That's going to be 1 plus alpha squared and minus 1 plus alpha squared over a. So this is what we have. Now we look at V1 of a. V1 of a is equal to 1 minus 1 over a, if you remember. And look at V2 of a. We try to find a pattern. That way we can set up the formula for Vn of a. So this is 1 plus alpha squared and plus 1 plus alpha squared over a. So what we see over here is that we see that possibly Vn of a is going to be a constant. We're going to call it An, and plus another, this is negative. So let me change the sign. It doesn't really matter, but it's better to use negative. So use negative sign. And so we also have over here, we're going to change this one to negative sign. Okay, and then we see something over here like Bn squared over a. That would be a good guess. And we have both An and Bn. These are constants. Constants depend on our alpha. Okay. So the computation we have so far achieved this part, the guessing part. So what we have now is actually a proposal for the form of Vn of a. And the next step is the essential one. So we are actually going to verify this is right by solving the system one more time. Okay. So we will do that one in our next video instead of this one.